Welcome to another episode of Robo Papers. Today we're super happy to have Zhecheng and Tianming with us here to present their papers called HERMES, which stands for Human to Robot Embodied Learning from Multi-Source Motion Data for Mobile Dexterous Manipulation. It's a long title because I think it's a pretty ambitious paper. They try to do many things in the same paper. But anyway, thanks for making the time, guys. Maybe as a start, maybe Zhecheng, you can start first and introduce yourself, and then Tianming.
Okay. Hi, Chris and Michael. Thank you for inviting us to join this podcast. I'm Zhecheng. I'm the third year PhD student in Tsinghua University. And my advisor is Hua Zhe, who is the leader of the Tsinghua Embodied AI Lab. And my research mainly focused on manipulations, and I will use some IR or sim-to-real techniques to solve the problems. Thank you.
I'm Tianming. I'm the first year PhD in Tsinghua. We are from the same group, and I mainly focus on the research of like simulation, sim-to-real, and some dexterous manipulation.
I'm super happy to invite to come here to present our work, HERMES, Human to Robot Embodied Learning from Multi-Source Motion Data for Mobile Dexterous Manipulation. Everyone knows that data is fundamentally important to the entire field of AI. It's also well known that robotics face a data shortage compared to computer visions and NLP. So the most common approaches try to solve data problems by collecting a large number of demonstrations with teleoperation devices. But this method is very expensive, especially for dexterous manipulation data. But actually, there's readily available big data source on the internet, so which is human motion data. We have enormous amounts of video data and mocap data sets, which are rich examples of human performing a wide range of dexterous manipulation skills. So converting human data to robot data would greatly ease our data bottleneck, but it's not that simple. We face clear challenges like the embodiment gap between the human hand and the robot hand. The human hand and the robot hand have different size and shape. It's also difficult to extract hand object informations from raw video. And we need to ground the kinematic trajectories with real-world physics, so the robot learns not just what to do, but how to interact with objects. There's an example. Even though we in the left this left video, even we extracted the kinematic motion, it is still far away from transforming into robot feasible data. The most direct solution is to use optimized-based retargeting, just like in the middle of the video. But this approach has a major flaw. Once you place the retargeted motions in a physical simulator and replay it, it always fails. As you can see, the hand didn't stop accurately and hold the teapot. So why? Because the process is purely kinematics. It contains no information about physical interactions. So how do we solve this? Our solution is to use reinforcement learning. We use RL to refine these initial behaviors by training an agent to maximize a reward. It will implicitly learn the physics of the interactions and produce a trajectory that is both successful and physically grounded. Actually, this process is similar to that of the locomotion. Many locomotion papers follow a roughly similar pipeline, extracting motion from videos, performing retargeting, and then conducting IO training. But I think the goals are quite different. Locomotion mainly focuses on to train a robust controller that is difficult to achieve with standard model-based method. It focuses primarily on the agent's own state information, but the manipulation involves reasoning about how to interact with the objects. So, and for manipulation, the actions are much more fine-grained than locomotion, so requiring much more high process and delegate operations. So for manipulations, you should not only care about the robot's own state, but also the object states. So we model the training process as the goal conditional IO. For standard manipulation tasks, reward engineering is complex and time-consuming. As you can see, the last two videos. This is in our last project. We conduct this reward terms by manually conducted from scratch. So as you can see, their motions a little bit weird, and actually there's a lot of drawbacks to manually conduct all details of the reward. For a single task, you might spend weeks designing and tuning task-specific rewards, and only to find they're completely useless for the next task. For example, if I just to given this reward, and this reward, I want to transfer this reward, this pour water reward to the pick up the cube. I think this will totally fail, since you have to tune a lot of new reward parameters. You have to balance different reward terms. It's a little bit hard to manually to get this reward. So this is why we need a new training paradigms for manipulations. Since the original method is not so scalable, we need to find a new paradigm. So our key idea is to use a unified reward to encourage the alignment between the pose of the robot's objects and the reference motion. So this is not task specific. I think this is more scalable ways to get the reward. So let's dive into our paper's detail. So the HERMES, it is a human to robot framework. So HERMES supports three types of data source: the teleobservation data, mocap data, and raw videos. We treat them as all as a trackable motion trajectory. So the first two form are direct, but for the video data, we have to extract the motion first. We use the off-the-shelf strong vision models, which is the foundation pose to extract the object pose, and use the Wheelers to extract hand pose. Yeah. Once getting the trajectories, as we said before, we will first retarget to the robot and then apply the IO to training. IO training to convert these motions to physically grounded. And to make the trained policies to more robust and spatially generalizable, we will augment every trajectory with various translations and rotations to effectively cover more workspace. Regarding to the reward, as I said, we will use the unified reward structures across all tasks, which is very general and not task specific. For this purpose, we have a object tracking reward and some penalty terms and contact reward to encourage robot to correctly interact with the objects. We also have designed a special term we call object-centric distance chains. So it will encourage the alignment of the directional vectors between the fingertip palms and the center of the objects in order to capture the dynamic relationship between human hand and objects. Our experiments show that our reward design is better than the baseline method under the same RL algorithm training, especially for handling 2 or 3 multi-object setting. So here's some other IL training details. We use the residual actions to the trajectory for robot arm. So our base actions are extracted from the reference motion. Yeah, so we will just train residual policies to refine its behaviors. And for our main experiments, we tried the out policy algorithm, DRM, on Mojoko, and also used the parallel simulator, MJX, to train the PPO. So this will show that our reward are general. We can also, there are some papers may say if we use different IO algorithm for the same task, maybe we should tune the reward parameters for each algorithm. Otherwise, the policy may not able to train well. But we find that these reward components we design are very general. We don't have to add or remove some reward terms. So after we train the state-based IO expert, we will distill a student policy for sim to real. We use the dagger to achieve this distillation. Also, we will use the scheduler to adjust the portion of the data in the buffer. So at the beginning, we will use the expert to roll out to get the training data. So the policy will be warmed up. We hope it can quickly to do more effective exploration. But as the training progresses, the reliance on expert rollout is gradually reduced, while proportionally increase the student policy participate in rollout. And we choose the depth image as the observation for student policy because the depth has a relative small sim to real gap compared to the RGB. We mainly so we, as you can see, the sim depths and the real depths are very similar. Yeah, we use some augmentation strategy to close the sim to real gap. Yeah. So here shows some how our robot to do a lot of tasks in the outdoor environments, which is very different from our simulation. Here more results showing the generalization ability. Actually, we are not
Sorry,
overfit to
Justin.
1. Yes. Sorry,
Sorry, Justin. I think I don't know whether it's just me. I think I'm still seeing the sim to real observation slide. I'm
Same.
guessing you might have. Yeah. Did you?
Yeah.
Are you still on that slide?
But yeah, I think the slide is not changed.
Not changed.
Yeah, it's still showing the
The
sim.
slides.
Oh, it just updated. I think it might have just
Yeah.
taken a while for the videos to cache or load.
Okay, so should I just stop sharing for now and check what's happening?
No,
Or
just give it a second. I think you just switched back. I think. Yeah. If you go forward again, I think it'll show up.
okay, is that work now? No.
I'm still seeing the sim to real observation slide.
Okay,
It popped up there. It's good. It just
okay.
appeared.
Now it shows.
Yeah,
Okay.
this
the
is
more
something
generalized.
PowerPoint does,
there
right?
are a lot
Like
of
if the
videos, so
videos
it's
take a
a
while to
little-
load, it's okay.
Okay,
Yeah,
okay.
right. Yeah.
Is that okay?
Okay.
In this.
Yeah.
In this slide.
Okay.
You can
Yeah,
see
yeah.
the video, huh? Yeah. Okay.
Um,
Okay, I will continually introduce. So here shows some how our robot do a lot of tasks in the outdoor environments, which is very different from simulation. Yeah. Have I switched to the next slide?
Not yet.
No.
I assume it's loading. So wait, so while it's loading, you talk about spatial and instance generalization. So how many instances did you train it on?
Actually, we had a data set called I forgot about that name. Just we have a data set, and there contains a lot of shapes of the instance. So during our trainings, we will try to actually I just changed its appearance. I didn't actually to change its shape a lot, and I also just to our instance set, our data set are all have the similar instance, so that it can just to use the similar grasp pose to grasp the instance. For example, to grasp the bottle, so the bottle cannot be so have much difference with the training bottle. So yeah, so the instance we just to let it have a, as you can see, these bottles have their size and shapes just have a little difference. So we can just to use the various, but it can just adapt to different heights. So we didn't change it a lot to keep the similar grasp pose. Yeah.
But I do have a question about the step one. So you have three different data sources, right? So teleop, mocap, and video. Could you comment a little bit about more about how much data in each of those you were using? Like what's the mix? And where do you source these data before you bring into the
Yeah, we have three types of data. So I think the teleoperation data is very easy to get. Since we have built the simulations, we just to add some VR devices, we can directly to collect a one-shot demonstration. I have to mention that all of our experiments, we only use one-shot human motions. We don't use we don't collect many human data. Yeah, so the teleoperation data is very direct. Since we build these simulations, we can easily to obtain the one-shot demonstrations. And for mocap data, we use the existing off-the-shelf data set called Alking. Some papers work on it. So we use this this off-the-shelf data set to get some mocap trajectories. And for raw RGB videos, actually we recorded by ourselves in our lab. Yeah. So we will use some, as I said, other modules to help us to extract the hand and object trajectories. Yeah.
And so on that note, for the other models you're using to reconstruct the object trajectories, like that means that you do have known objects then. So is that how strict do you think there's a way you could reduce that restriction, or
sorry?
So like the model of the object that you're using in Sim, does that have to be a known object? Like could you talk about that assumption? So like I couldn't just use videos from YouTube because I probably don't have like a
I
model
see.
of that particular like model.
I see.
Like
Okay.
yeah, right. Okay.
Okay. So first, we need to use the AR code to scan our objects.
Okay. Yeah.
So I want to use some extra tools to scan the mesh and put it to the to the simulations. Yeah, and then actually the mesh. We have to tune a lot of simulation parameters. So we will also use some primitive shapes to approximate the shape of the objects so that it can simulate smoothly, especially when
I think you just
with the hand.
mentioned like from like YouTube videos, like something or other to get the object mesh. I think it's quite. I think someone there's a lot of papers investigating into this problem. I think they do some like reconstruction of the interaction of the hands and manipulated objects. I think there are some computer vision papers are actually doing this. I think the results may be not so accurate nowadays. So, but I think it's like a promising way to like scale up the data in the future. I think
Yeah.
it can be
For
applied to
now, we
our
use
pipeline.
the AR code to scan the mesh by ourselves. But actually, I think in the futures, there's some computer vision papers trying to directly to extract the mesh and the object pose from the raw video. Yeah. So, but it's not. It is, as Tammy said, it is not. We tried it, but we think this is not so accurate. But maybe in the futures, it can
But
work
it's
well.
getting better. Yeah, that makes sense. Yeah.
Okay. Since our robot already demonstrates generalization ability across diverse visual scenes, we decide to equip it with navigation capabilities as well, enabling it to autonomously perform both navigation and manipulation skills in open world environments. So for manipulations, for navigations, we use Vint, this image goal-based navigation model, which can operate solely on RGB images and supports long horizon in the wild navigations. Vint also demonstrates effective zero-shot generalization capabilities without tuning the model. But for most of the manipulation tasks, moderate discrepancy between the robot final pose and the target pose can lead to the manipulation policy fail to finish the task. So, for example, if I let the robot face the front of the front of the tables to collect the data and do the policy, after navigation ends, the orientation is skewed, then policy will most likely fail. So Vint does not guarantee termination within a sufficient tight error bound. To address this, we introduce a local refinement step after Vint completes the navigation. We call it a closed loop perception PMP localization algorithm is employed to adjust the robot pose, ensure closer alignment with the target pose. So how do we do that? We first will use a neural feature matching module called efficient lofter to detect the correspondence between the current robot captured images and the goal image. And next, the detected features are lifted to 3D space. This yields the 3D coordinates of the match features. Then the PMP will try to minimize the reprojection errors between the robot current views and the goal pose. And he will just to give us the transformation measures, tell the robot how to move to the target pose. Here, there's some pictures about how the closed loop PMP adjusts the robot step by step. And as we can see at first, the positions will being stopped still differ from the target positions. But after several iterations of PMP refinement, it become much better aligned with the target pose. Yeah. So finally, is our the whole pipeline. So which first we train the IL experts using multi-source data, and then we will distill it to student policy. And next, since our models has the generalization ability, we also equip it with navigation models, and hope it can have a precise localization. Yeah, so all these pipelines can combine all these things. We can let our robot to have a generalizable sim-to-real capabilities and to manipulation in the wild visual scenarios. This is a short videos showing how the robot autonomously navigate and manipulate in the convenience store. Okay, so at first, this is Ving's parts. The red line in the videos, it's a little bit here. The red line, the red line here is the on the bottom right is the Ving of the action of that the Ving to infer in real time from the current visual input. Okay, so just slow a little bit. When the Ving stop, it will calculate how the distance between the current view and the target view. And after the closed loop PMP adjustment, and we will transfer to the manipulation part. And as we can see, when we randomly to pick the bottles on the tables, and he will just to successfully to complete this scanning path. Okay, so my
Can I ask?
over.
Yeah, can I ask so like during this test, like what is being instructed to the model? Is it
okay? The
is
structure
it
of
like
the
like what is the instruction given to the model? Is it a go
okay.
image?
We didn't get its explicit instructions. So for Vings, we have to first to record the trajectories first, and it could be long horizon and in the wild. So we have to record the trajectory first. So we have the Vings. So when we finish to record this trajectories, and it can the models can autonomously to navigate according to the current views, images, and the go images from the recorded trajectories. So the Vings will start to running at first. Okay, but when it's stopped, yeah, the Ving has some termination conditions when it's when the Ving thing is stopped, and we will you know there will be some difference between the Ving stop pose and our desired target pose. So this is the there's some gap between the target pose and the Ving stop pose, and then the closed loop PMP will work, and it will adjust the pose. Yeah, well, and also there are some threshold, there are terminations conditions. When the Vings, when the closed loop PMP find that there just a small errors, and he will just stop, and we will just to autonomously switch to the manipulation policy.
Got it.
Do you have a feel for the accuracy of the closed loop PNP policy? Sorry, Michael. So I noticed like you showed images. So if anyone's listening, you can't see this, but like the difference here looks really small. Like from the robot's point of view, a couple slides ago, it was hard for me to tell the difference. So how which is pretty impressive. So how do you know how accurate it is, or what kind of distances it handles?
Oh, so you mean how accurate the closed loop PMP can?
Yeah.
I think it is very accurate from our experiments. It may have just 1 or 2 centimeters errors. Yeah, actually we had experiments in our papers. Yeah, we conduct this experiments in outdoor things and in indoor things. Yeah, I think the error is very small, but maybe for the navigation, it's still a little bit big for this error. But I think for manipulation, it's enough.
A couple centimeters is definitely, so that's definitely, like, I guess, within the range that you can easily randomize in the RL training and simulation. Is that kind of so that amount of error is easy to account for? Okay, cool. That makes sense.
That's all. Okay, so if you have any questions, we can check the papers or check the website, or I can just roll back to the slides that you may have some questions.
Yeah, so I would say, like, firstly, like, this is, I don't know whether, Chris, you've seen other paper that actually it's a combined navigation and manipulation to this extent. I thought it's pretty ambitious.
Maybe I to stop the slides, I can transfer to the...
Yeah, the website, you have a lot of cool videos, actually. Yeah. Yeah, I was just saying, yeah, it's it's quite amazing to me. You combine like a basically a fairly long horizon navigation, and then you do this PNP closed loop thing to make it like to make the transition into the manipulation task tractable, right? Because usually Vint don't care about the manipulation, so they would just stop at maybe even 1 meter away, right? But 1 meter, it's the difference between being able to do it and not being able to do it for manipulation. So
Okay. Yeah.
it's very cool that you managed to do this in a single paper. Yeah, so I guess I'm curious about, I guess going back to the data mix, right? Why do you, for example, or did you try any ablation study where you don't use mocap, let's say, just have video and teleop? I'm trying to get a sense, like for example, how much of that, like of does each of the, your modality actually help you out of the three?
Okay. So I think the data quality is the teleoperation data has the best data qualities, and the next is the mocap data, and then is the the human motions from the extracted from videos. It since the mocap data and the television data. So the television data is very direct, and the mocap data they will use some markers or some mocap systems to capture the object pose and the human hand pose. So there are just some maybe embodiment gap between the human hand and the objects. But for the videos, we have to rely on the other extra vision modules, for example, the foundation pose and the wheeler to extract the hand pose and the object pose. But when we, for example, when in our experiments, when we extract the wheelers will just to the hand pose extracted by the wheelers, there will be some jittering actions, so it is not so smooth. So when we do conduct the sim to real, these jittering actions may lead to some OD state, and it will lead the whole sim to real file. Yeah, and for the I think so for the foundation pose, when we just to record the videos, we find that if we match some symmetry objects, it will just rotate along one axis, and we have to do some pre-precise to remove these rotations. Or even a more serious situation is that it is not quite well to handle the occlusions. So when our hand and objects, when the hand grasps the objects, it might have some, just to not so accurately to estimate the pose of the objects. Yeah, so I think the videos will be mostly most challenging.
So maybe I need to do like a bit more explanation. Actually, we did not mix the like 3 data sources up. So we just use one motion, one human motion trajectory for one task. So we don't mix them up. And about the data quality, Zhecheng said teleoperation data is the most easy one to like track by a RL agent, mocap, and then the video. The video is relatively a harder one. So yeah. So we actually didn't mix them, just one motion for one task.
Yeah, I know there
But
are some general motion trackers just in locomotions. Maybe there for locomotions they can just use one models to track different reference trajectories. But I think that it is quite challenging for manipulations. For example, I think our HERMES, these pipelines have the potential to do the offline teleoperations. So maybe in the futures, people don't have to wear some teleoperation device to near the real robot and to do the teleoperation to collect the demonstrations. Maybe in the futures, we can just record the videos and upload it to the simulations and to maybe somehow train it, and we can directly to let the robot to have a generalizable actions that can to finish the similar behaviors of the humans. But but it's a little bit quite challenging for the locomotions. The only thing you care about is the robot's own state informations, their own state. But for manipulations, you also should care about the object state. As if we just record the videos, actually we don't want to the objects in the front of the robots and in front of the humans are the same, right? So we hope it can have some generalization abilities, have some spatial generalizations. We just to put the objects in a certain positions, and the robot can just to have the generalization abilities to pick it anywhere in the workspace. So this is a little bit hard if we want to train general motion trackers of the manipulations. Yeah. So it is not only have the robot own part, but also we have to care about how to interact with the object.
Yeah, got it. And just to clarify, when you say teleop, you don't mean like a robot teleop, right? You mean literally, I saw Apple Vision Pro. So you mean someone wearing Apple Vision Pro. So in some sense, this is also credit to their phenomenal like hand tracking and the AR kit. Okay, got it. Yeah, I imagine you may not be as accurate with some other, let's say, like VR device. Okay, got it. Yeah. I know that you guys have some like further down the website. You have some videos with failure cases. Like I think it would be interesting if you can walk us through a little bit and what you think of them.
Okay, so I think the failure case mainly from the two part. Maybe one part is from the navigation. So there's also some where navigation will have some not so accurate. So maybe, but I think in most of the case the navigations are accurate. So for the most of the failure cases are from the sim to real. I think for the manipulations sim to real, we should focus more on the how to narrow the perception gap. So even we use lots of augmentation strategies. We use data augmentations. We use depth map so that we don't care about the textures of the objects, but we find that there is still some gap between the sim and real from the perception aspect. Yeah. So I think this is the main reasons that it can cause some of the failure cases.
So you're mentioning texture, but I thought you were just using depth images, right? So do you mean like physical texture, like friction, or?
So the physical friction.
Yeah, because like it can't
I think
distinguish like visual texture, right? Or sorry.
I think just means like although we use depth map, we don't really care about textures. There are still some like gaps in the wider scenarios because the background that is in there.
Yeah, makes sense.
So how could we narrow this gap? I think it's not quite. We don't use some very tricky strategies. We mainly apply three types of augmentations. The first one is the depth clipping. We clip all depth values greater than a certain threshold. And the second one is adding Gaussian noise and making some Hall fillings to simulate the sense noise and feel the missing depth range. The second one, I'm not sure whether it is useful. I use a mix-up like operations, just like we will have a depth data set, and we will just to extract a batch of the data, a batch of the depth images from in the wild data set, and to mix up with the current simulation images. And there was a portion, and I think this technique is very common in for training some images for RGB sim to real or for some supervised learning. But what do we want here is to have a more diverse noise distributions, so that we try to mix up the in the wild data set. So we hope it can handle some different noise distributions, since the Gaussian noise can only solve the Gaussian part, but for the other distributions, we hope it can also have the abilities to handle.
Yeah, I guess my question is for how do you so-called get the real depth here?
We'll directly use the real sense cameras to capture the depth image.
Okay, got it.
Actually, okay, there's also another stories. Actually, first we wanted to use the depth anything, these kinds of foundation models to try to. Okay, also we have ablation studies here.
Just using computer vision, is it?
Yeah, we use the depth sensing V2. This is the depth images produced by depth sensing V2 from the simulation, and this is produced by also generated by the depth sensing V2 with the real world images. As you can see, these two are also similar, but we find the experiment results are not good. The generalization of words is very bad. So, but we found so the semantically they are similar, but when we plot this intensity distributions, there are still some gaps between the depth images generated by the estimated by the real world data and the simulation data. Yeah. So I think there's some. Yeah. Okay.
Yeah, depth anything is only monocular. Is it just using one image and then infer the depth, right?
Yeah.
Okay.
So I think
see.
Yeah, maybe there are some other advanced depth estimation models can. Yeah, there's some recent papers. Yeah, Tianming just sent me another good papers to do the depth estimations. Maybe it can help a lot to. So maybe we don't have to add to manually. Although I think our augmentation strategy is not complex, but if the depth models can help us to remove all kinds of augmentation, I think that would be better.
Yeah, but I think another problem, the depth estimation models, like they're really like relatively slow for manipulation tasks because like depth sensing, we use some like TensorRT to accelerate the model inference, or it will be like just like I don't know, less than 10 hertz per second, so it's hard to directly use it in manipulation tasks. I think manipulation, the depth sensing V2 is like the faster one. There are some like diffusion-based molecular depth estimation models. They're even slower, just 2 or 3 FPS. The model inference is so slow. So I think there is a lot of problems to tackle. Like if you want to use like these foundation models.
Yeah, we need the computer vision guys to work harder for us. I do have another question though. You mentioned some of these like rewards that you guys have like set, right? And you could you comment a little bit? Like I saw something about some penalty terms, something about like tracking object. Like could you comment a little bit like how you end up with those, and like for example what other rewards have you tried that you think it just doesn't work? Oh,
Okay. Maybe Tianming can talk a little bit about it.
About the like reward design. So first,
yep.
I think the maybe let me see, the most important one, the object distance chain that we propose. So it's basically the alignment of the directional vectors of the hand palms, the hand fingertips between the objects, center of the objects. So this is basically like just you transform the hand hand access to the object frame. So it's object centric. So you can do some like transformations and rotations to the whole trajectory, and the reward also remains the same. So it's like a like a reward you can use across all the like tasks, all the trajectory augmentations. So this is the object distance chain. Another one is like really important. I think is kind of there's a hand pose reward, hand Q pose reward. Q pose, I mean the joint angles of the hands. We encourage the like hand joint angles to be close to the like reference trajectory, but actually it cannot be so close. Otherwise it will totally imitate the trajectory, and it cannot learn the interaction the object with objects. So, but I think if you add this reward term, it can greatly accelerate the exploration. So if you don't add this reward to the reward terms, the RL training will be very hard, very slow. So this is important for exploration. And I think another one is like the penalty terms. We use some like talk terms to action penalties to like make the trajectory, learn the trajectory more smooth. and not so jitter. So we can actually do sim to real, and we can deploy to real robots.
Got it. I suppose for the first reward, like it will probably only work for more rigid objects, right? I guess.
Yeah. There is
Yeah.
experiments. Yeah. So we have a baseline master. It may mainly use the object tracking reward, and it can. I think the most important reward, the basic reward, the most basic reward is the object tracking. So if we want to finish this task, we have to track the objects accurately. So yeah. So the baseline method is to just track the object. It's called ObjectDex, another very good paper. So but we find that if we want to tackle with multi objects, the tracking only the object reward is not enough. But if we just add the object centric distance chains, yeah, it can work well in multi object tasks. For example, the clean table, we will we'll pick up twice and to place the tables in front of the robot. So yeah, this is one task, and another one is the portees. We will to handle two objects, and actually the portee this is extracted from human videos, and so there are some noise and some jittering actions. So if you just track the objects, it's a little bit hard since our reference actions is the base actions. So if the base actions have much noise and have some jittering actions, so it will be a little bit hard to finish these tasks. So we found that the object-centric chain distance reward term can help you to alleviate these problems. Yeah, so it can also help you to get a more smooth actions and also to track the multi-object accurately. Yeah.
Yeah. Could you share a little, maybe zoom in this a little bit? So you have this comparing your method with, I think, the one that you just mentioned, ObjectDex, right?
Yeah.
So for example, I'm just eyeballing it, right? Like Paul teapot for human video.
Yeah.
So basically the y-axis is normalized episode length. Presumably, the faster you get to 1, the better.
Yeah, the one the better. The one means you just to follow the whole trajectory.
Mm-hmm. I see.
And just like because of the jitter, the ObjectDex is just clearly not even able to accomplish this at all. Like the trajectories.
Yeah, I guess. Well, I guess Chris, maybe you can ask the question again. I don't think he heard it.
Well, so clearly like this the blue line. So the baseline trajectory here is just completely flat. Like it doesn't make any progress on this task at all. So this I guess I'm trying to understand why it can't make any progress.
I think the main reason is that it will has much jittering actions.
Okay.
It is the task that has the most noise here.
Gotcha.
Actually, in our sim to real experiments, we also show that if we also for this task we use some extra real world rollout trajectories to fine tune the policies. We use five real demonstration five rollout trajectories from the policies to fine tune the policies so that it can make the sim to real achieve the sim to real. Otherwise, it will have some jittering actions that it cannot.
So by jittering actions, though, so you said this is tracking the object-based pose, right? So that means that because it's a human video or because there's lots of occlusions or something like that, then you're like the pose estimate of the teapot is jittering during this video, and that's what's making it hard to imitate.
I think the jittering comes from two parts.
Okay.
One is the object, and one is the hand object. The hand. So the hand, actually the hand pose estimation module also not so accurate. So they will just cause some. Yeah. Also, okay. And another part from the noise is from the simulations. We have to accurately to model the collisions. So I think this is the main problem. The sim to real is just a little complex, right? So you have to model your mesh, your objects accurately. So the collisions between the hand and the objects will might be processed. Otherwise, it just some shaking. So I think the simulation also have some, it will also contribute to the jittering noise.
So this is
a
because
little
there's
bit.
a closed like grasp around in that,
Yeah,
and
yeah,
only that
maybe
one. This is closed grasp around a narrow part of a large object, and that's very hard for
Yeah,
the
maybe
simulator.
they
So that
do.
kind of, yeah.
Yeah, they have to use another, just some jittering actions to stable the grasping.
Yeah. That makes sense. Yeah, that real to sim to real part seems like it would be the most, like getting the robot object model, getting the physics right, and then getting it all back into the real world. Seems to me like it would be the hardest part of this whole thing. That's makes sense.
Yeah, so the real to sim to real still has a long way to go. So, but I think it has a lot great potentials to really scale up the data. But for now, maybe the simulation guys should to give us better simulations, and the computer vision guys should give us more better estimation modules. So actually, we are also a little bit confused. If we directly collect the data in the real world, do the imitation learnings, actually, I think most of the tasks just can be achieved. But for if you want to finish the task in a real to sim to real plans, it will be a little bit complex to achieve that.
So okay, since you said that, so you said you think that if you just collected it in the real world, it would just succeed. So why do this then?
Yeah, but as I said, if we directly to collect the data, so it's a little bit expensive. So it is not quite easy to scale up the data. I think the simulation has the potential to scale up the data better, especially for robotics.
Yeah, I would expect that what you do has better generalization, right, than collecting it in that scene. Yeah. Okay. Is that what you would expect too?
So basically, why we do this is because we actually collect the mockup data and the video data. That's because you cannot directly do that in the real world, right? You cannot directly transfer mockup data like directly in the real world. You have to use like simulation as a bridge to do this. So I think video data and mockup data, it can have the potential to scale up. Yeah, I think that's the main reason.
Also, the teleprediction can. We only collect just one shot. We can use some augmentation method in the simulation very easily. We can get a lot of privileged information to help us to train.
Yeah. All right. So I guess a typical question to wrap things up, maybe one or two questions. So, I mean, if you guys have, let's say, maybe 2 or 3 months more to this project, like what would you want to like squeeze into this paper?
Okay. Yeah, I think from my perspective, I think there are two things that the very challenging things of the sim to real should do. The first, I think our papers make the reward design scalable, but there are still some things should be scalable for sim to real. One thing is the how to set up the things very quickly. For example, if we want to build things in the simulations, we have to create the assets, create the bugs, or to use the primitive assets to create a lot of simulation. We have to create a simulation asset first. So it is not quite scalable. But in contrast, for the real world, you don't have to do that. You just to move your robot in front of tables and to use your maybe Jello, or you can directly to collect the data. So I think the first thing or the sim to real guy should do is to make the scene configurations, scene setups to be scalable. For example, if we can just to go to one rooms and to scan the whole rooms, maybe use some 3D Gaussian splatty, some this kind of techniques to quickly to let the things to be imported to the simulations, and also it should have autonomously to segment each component, each mesh, so we don't have to tune the physical parameters. We can directly to get this mesh and get the collision correctly. Yeah, so I think otherwise you have to manually to import every mesh and to manually to tune some physical parameters of the mesh, of the collision mesh of each object. So it is quite complicated. So I think the first thing we should do is to handle how to make the real to sim to make very very fast, to have a better pipelines to configure the whole scenarios. And the second one is to handle the deformable objects. The sim to real for most of the, I think for almost every sim to real task, most of them are or can only handle the rigid body. The reason is that the simulators, the existing simulators cannot simulate the deformable objects well. So, but for the for in real world, I think these embodied AI techniques, their advantages is that we can handle the deformable objects well, since the pose of the deformable objects is very hard to estimate. So we cannot use some other pose estimation or some other modules to estimate the pose and to do the motion planning to grasp the objects. So for deformable objects, the simulation should for simulating the deformed objects, the simulator should do better. Yeah, I think this is the two main obstacles to should be overcome in the future for sim to real. So if I think the real world becomes scalable, the sim configuration becomes scalable, and we can handle deformable objects, I think that in that moment the simulation can really to show its power.
Well, I guess I mean you mentioned, just to double tap on the real to sim thing, right? Let's say even if you have all this, okay, you just take one video, you scan the whole thing to convert it into some Gaussian splat with the mesh all nicely done up, segmented and whatnot. I wonder, like, I'm just looking at my laptop, for example. If you scan it, you would think that this whole thing is like that, but obviously we all know the laptop can be folded. It has its own weight, it has different slippery. So I wonder whether is this still going to be sufficient? You see, yeah. I mean, some things are a lot more heavier. Something. I mean, not to even talk about deformable object. I'm just saying things that are, because of the texture and maybe the center of gravity of that particular object. It may not be able to just eyeball it for some things. Yeah.
Yeah, maybe we also need some maybe LLM or VLM to help you to design these parameters, these physical parameters. Yeah.
I just feel like ideally it's a loop, right? Like there was some sim to real work from NVIDIA a very long time ago that it's like estimates it, trains a policy, tests the policy, gets new data, and so on. But like that's far outside the scope of anything that you're doing, right?
Well, that's an issue though. Right? Once you test the policy, if the policy breaks some stuff, and then the whole thing will to stop. Every time you touch reality and then you testing reality, things break, and okay, gosh, you gotta reset. Okay. Yeah. Okay. Cool. Very cool. Yeah, I guess maybe just to wrap things up, maybe Tianming, do you have any maybe additional thing last things you want to say? Like what have you learned from this paper, or what you want people to take away?
Oh, okay. Maybe from my perspective, I think if you want a simulation to like really release its power, I think there must be a way to Zhecheng said a sim to real to sim. But I think, like from another perspective, there should be a way to automatically generate things or the manipulated objects in simulation, because that's a very, very low cost way to get the data. So I think that's a biggest advantage compared to real world, because you can really get low cost data in the simulation. Yeah, I think this is another perspective. Maybe I will like find a way to directly import some mockup data sets or video data directly into the simulation without you specifically to tune the physical parameters or the collision primitives of every specific thing of the simulation. Yeah, maybe I will find a way to do it in the future.
Yeah, I guess I mean my thought about simulation is that I kind of feel that there's nearly infinite things that you can simulate. Like for example, if you want to so the search space becomes so nearly infinite. So obviously compute is still finite. There's only that many GPU we can have access to. So Uh, yeah. So that's why I think it's actually. I actually think that the bottleneck to using simulation oftentimes is not just having to compute, but it's actually having people like yourself who know actually how to use the compute well. Otherwise, you'll be simulating a bunch of scenarios that have very little, let's say, distribution overlap to the real distribution we care about, which is in the real world. And also at the same time, miss out actually things that should happen in the real world, but because, yeah, so, yeah. Anyway, that's just my thought about simulation. Like in theory, it's very cheap and very powerful. You can speed up time maybe 1 billion x, maybe even more. But 1 billion x versus like nearly infinite source space is still tiny. Yeah. So,
Yeah. I think that for now, the Zhecheng module code is one type of simulation, simulators. And actually, I think in the futures we can use the word models. This is kind of the data-driven simulator. It's just a general simulator. Maybe we can in the futures we can train a lot of things in a word model. So maybe it's in this word model, since this is data-driven, you can simulate it better. So it's just like the deformed objects or some real-time sim thing is very easy to do in these kinds of word model.
yeah, I mean, sorry, going off on a tangent, but like I'm very bullish on world model as well. But like you say, it's very data hungry. You need a lot of data to even train it in the first place. But I suspect in world model, because it's so different from a classical simulator. In classical simulator, you have all the privileged information. Here you're back to like it's something same as video. Like you have to infer action. You're gonna have some embodiment gap. Yeah, so I suspect it's you have the same kind of bottleneck with video, purely video data. We might have it for one model again. So yeah, but yeah, I think one model will be extremely useful. Mm-hmm.
Yeah, I think maybe world model is like, in my perspective, harder than the really good manipulation policy. I think it's much more data hungry. But I think there is kind of another type of data-driven simulator. It's like partly data-driven. It just replaces some physical laws of the like some like iterative solving the process in the simulation. They replace it by some data-driven like neural networks. Just to replace some physical laws of the simulation and not the whole simulation. They change it. So I think this is also a like promising way. They can like, for example, collect some data and they know how the friction of the table is, not how the robot arm will move.
So very structured prediction, right?
Yeah, actually.
Yeah,
right,
but I
guess.
think
Sorry.
Okay. I think the word models can use more data, use more just like video data in internet. As you can see, train the word models, we don't have to use customized robot data. Yeah, we can just use many video data to train the word models. Yeah, I think So, actually, I agree with your opinions that we can first just to use the word model to replace the physical laws of the simulators, and but I think as the word model becomes better, as you can see, the Sora 2 just comes and it can really generate very realistic videos. So, I think it has the potential to maybe. For example, we can first pre-train the policies and then use the pre-trained policies to generate some data and to tune the word models, and it can help you let the word models to help you to get a better policies. Yeah. So our goal is to improve our policy improvements. So I think the word model or the simulations is a very effective way to directly to interact with the real world. We can have simulations, we can have models that we can interact with them, so we can just make everything cheap.
All right, cool. I guess yeah, just to wrap up the whole episode, like our last typical question, is there any paper you guys came across recently that you want to give a shout out to? Any cool paper that you think people should read? Doesn't have to be real to seem to real. Could be anything that inspire you guys.
Okay, I think in the next week, our lab will just publish some very exciting papers, and you guys can check it out.
Okay, well, I mean,
right.
What is it? Like? I mean, because by the time this episode goes out, your paper will be out already. Could you share like what is that paper about?
It is not. It is still not archive. I mean, maybe in archiving next week. It is about some real world IO. You can directly to train the policy use the real world. I think I think in the last robot papers, you invited the Q Chongqing.
Yeah.
So I think this is a very good paradigms. We have a pre-trained policies, and we can do some offline to online things, too. And you also said that maybe we can try some real world IO based on pre-trained policies. And I think the next week, our paper is just like that. Yeah,
Very exciting.
we have offline to online, but not. This is not my papers. It's from our lab. It's about some pre-trained to offline to online, and we have some real world online tuning about it. Yeah.
Cool.
Cool.
We'll definitely watch out for that. Tianming, any paper for you?
I'm always reading some like Centurion related papers. I think it's hard to really recommend one.
Yeah.
What's the best sim to real to sim kind of work right now, in your opinion?
I think everyone is like trying to find a way to like make Centurion really useful. I think there's still not an answer.
Okay. We
I like
just
the honest take.
have
That's good.
a lot of shortcomings of sim to real,
Yeah.
but we do sim to real. I hope my reviewers.
It's an important thing to be working on. It's good. If it worked, it wouldn't be exciting. All right,
Yeah, it wouldn't be research if it would completely work, right? Okay,
Yeah.
cool. Yeah. Well, anyway, thank you so much for making the time, guys. Thank you for spending more than an hour with us. I think Chris and I learned a lot. Cool. Well,
Yeah.
definitely looking forward to that paper from the group. And I guess I'll see you guys in Hangzhou really soon.